In this video, we look at another application of dot product and cross product to find the volume of what's called a parallelepiped. So a parallelepiped is, I think, of a rectangular box, but instead of having rectangles as all of the faces, it has parallelograms as its faces. So if we're talking about a parallelepiped with the vectors u, v, and w as adjacent sides, it might look like this. So here's my vector u, and maybe this is my vector v. And then together, these two form the base. So u is back here again, and v is over here. So this is the base of my parallelepiped. And then w is some third vector, and it forms that third side. So there's w, and parallel to that I should see another w. Oops, I guess it needs to be a little bit longer. And then u is going to be back here. So I've got a parallelogram with u and w as sides, I've got a parallelogram with u and v as sides, and then we'll also have parallelograms with v and w as sides. It's a little hard to get the perspective just right, but we'll try. Looks like a squished box to me. Here we go. So I've got a bunch of parallelograms as sides. Well, the area or the volume of this thing is exactly what you would expect. It's just base times height. So we need the area of the base times the height of this guy. And the area of the base, well, that's just the area of this parallelogram with u and v as adjacent sides. So the area of that parallelogram, we know that that is the magnitude of the cross product. The cross product of u and v. So we find the cross product of u and v, we find its length. It turns out that's going to be the area of this base. Now you say to yourself, okay, well, what about the height? What's the height of this thing? Well, the height of this thing, it's like this distance right here. I need that to be at a right angle. It needs to be perpendicular to the base. So it needs to be perpendicular, to the plane containing u and v. That's important. And it also has to involve the projection of this vector w onto that. So first, let's just find this vector that is perpendicular to the plane containing u and v. Well, I know one vector that is perpendicular to the plane containing u and v, and that's the cross product. And if I use the right hand rule, if I put my fingers toward u and curl them toward v, it looks like if that is my plane back there, the vector pointing up, that's going to be u cross v. So here's u cross v. I don't actually want u cross v. What I want is, and that's probably the wrong length, but you're just going to calculate u cross v. You're going to get some length. You're going to have that direction, it's going to have some length. Turns out the length is equal to the area of that parallelogram, the base. I know, it's amazing. But you don't want this whole length here. That's not the height of your parallelepiped. The height of your parallelepiped is the length of the projection of w onto the cross product u cross v. So the height is this guy, that distance, and it's going to be the length of the projection of W onto U cross V. You say, holy moly, that's a lot. That's okay. We actually have all the pieces that we need to come up with this formula. So I've got that times this. Well, what was the, how did we find that formula for the projection, or the length of the projection of U onto V? Well, remember we had something involving the dot product? We said, let's take the dot product of this vector with this vector. So we're doing W dotted with U cross V. And then we're going to divide by, we're going to find the absolute value of that. Dot product is a number, absolute value is a number. And we're going to divide by the length of U cross V, the vector that we're projecting onto. This is just an application of the projection onto U, of U onto V, where W is playing the role of U and U cross V is playing the role of V. And if you want, you can go through the trig again and prove to yourself that this is equal to this. Okay, well that's cool. It's very cool because look at this. Those two reduce, and we get this beautiful formula right here. Who knew? So if I want the volume of this, all I have to do is find the cross product of U and V and then dot it with W. And this is what's really cool. I'm actually not going to show you the derivation of this part, but it turns out that the dot product of W with U cross V looks like this. Sometimes this is called the triple scalar product. Whatever vector is first here, you're reading left to right, its components go in the top row. The components of this next vector go in the second row. And the components of the last vector go in the third. Then when you evaluate this 3 by 3 determinant, it's a true determinant because these are all numbers, and you're going to get a number out. The absolute value of that number is the volume of that parallelepiped that we started with over there. And we could, use algebraic definitions to prove that if I take this and I dot it with this, I get this. But I'd rather not. I would rather just state this for you, and if you really want to know, come to office hours and I'll show you how these guys are equivalent. Okay, so let's say I want to evaluate this 3 by 3 determinant. You can expand along any row you want. We have a tendency to expand along the top row because we're comfortable with that because of cross products. Don't forget the sign convention, plus minus plus. So this is what you're going to do. To get the number, it's not a vector this time, it's a number. You're going to have plus W1, whatever that is, times the 2 by 2 determinant that comes from crossing out the column and the row containing W1. So it's just like when we did cross product, but instead of multiplying by I hat, you're multiplying by a W1, which is a number. So you're going to have this over here. And you're going to do minus W2, cross out that row and column, and you're left with U1, U3, and V1, V3. And then cross out this row and column, you have a W3, and then you have U1, U2, V1, and V2. Now I'm not going to go any further, but you can evaluate those 2 by 2 determinants, and then you do a bunch of arithmetic, and you're going to get a number. And the absolute value of that number is the volume of that guy. So let me show you an example. I guess one other thing. It turns out you can change the order on this if you like. You could also do U dotted with V cross W. That will work. So you'll have U, V, and W here. Or you could do V, W, and then U. Or like we did W and then U and then V. All of these guys are the same, and the only difference is which row they end up in. Now there are other possibilities, like you could flip some of these, like you could change the order. We don't want to change the order. So it's UVW or VWU or WVU. It's like you took this UVW and you kept sliding it. So you got rid of the U, and then you put the VW first, and then put the U on the back end. And then you get rid of the V, and then put the W first, and put the V on the back end. So you're just sort of like switching the positions on these guys without like flipping the order. We don't do like W and then V. You see how it always, the only time W comes before V is when there's that space, that U in between them. Okay. So keeping that in mind, let's apply this. So let's say I have a parallelepiped with sides, adjacent sides given by the vectors U, V, and W, and U has components 3, -5, and 1. V has components 2, 0, 2, and -2. And W has components 3, 1, and 1. Now I could use the expression from the derivation up here, but I'm just going to use U, V, and W in the order that they're alphabetical order. That'll work just fine. So if I want to find the volume of the parallelepiped that has these 3 as the sides, so that you've got 2 that are going to give you your base, and then the third one goes up from some perspective. It turns out we just evaluate this 3 by 3 determinant. So we cross out the row and column containing the 3. Then you've got 2, -2, 1, 1, because we're crossing that out. Then you're going to say minus a -5. You always do plus, minus, plus. You change the sign on that middle term. So you have minus a -5, cross out the row and column containing -5. So you have 0, -2, and 3, 1. And then you have last is 1. Then you have 0, 2, and 3, 1. So let's do some arithmetic. You've got 3 times 2 minus a -2 is plus 2, plus 5 times 0 minus a -6 is plus 6, and then you have 1 times 0 minus 6. So I'm running out of space. That's 3 times 4 is 12, plus 30 minus 6. So I've got 36 there. So what is the volume of the parallelepiped that has these sides? 36 units cubed. And that's it. So it's actually pretty simple. It's just evaluating 3 by 3 determinants. You can actually expand along any row you want. We tend to do this top row, but if you wanted to, it would make sense. You'd save yourself just a tiny bit of work if you expanded along rows or columns that contain zeros. So we went this way, but because of that 0, I might just as easily have gone this way. The sign convention goes plus, minus, plus, and wherever you ended there, pick up where you left off. That was a plus, so the next one's a minus, plus, minus. That was a minus, so the next one's a plus, minus, plus. So if I wanted, I could expand along this row, cross out the row and column containing the 3, do that 2 by 2 determinant. And then I have minus 0 times something, doesn't matter what it is because it's multiplied by 0, plus 3 times this 2 by 2 determinant. If I do that expanding along this column, I should still get 36. I was going to finish this video, but let's do that and prove that we get exactly the same thing if we expand along that other row as well. Now those signs only apply to the ones only applied to the factors that we're multiplying by when we expand. So we're expanding here, so we have plus, minus, plus. Cross out the row and column containing that entry. So you have 3 times, you have 2, negative 2, and 1, 1 there. Then we're going to subtract 0 times something, but it doesn't matter what that is because we're going to get 0. Then we're going to add 3 times something. Cross out this column and this row, and you've got negative 5, 1, and 2, negative 2. Should get 36 either way. Shouldn't matter which row or column we expand along. So we still have 3 times 2 minus a negative 2 minus 0 plus 3 times 10 minus 2. So 3 times 4 is 12. This is 3 times 8, which is 24. And 24 and 12, that's 36. Same thing as I got over there. Oh, very good. Same thing either way. So volume hasn't changed, formula hasn't changed, and we've just demonstrated that at least with this matrix, you can expand along any row or column you want. Actually, it's true all the time. You can pick any row, and if the row or column has a bunch of zeros in it, that's where you want to go, because then you're going to have entries like this that just disappear, which is always nice.